This lesson is part 2 of section 7-9, graphing rational functions. We're still going to graph functions today, except for now we're going to go into a lot more complex examples. So we'll start with number 1 here, which has already been factored for me, so I can jump right in to find the holes. Now obviously, since we didn't cancel any factors, there are no holes. Okay, so there are none. Now for the x-intercepts, I'm going to let y equal 0, but when I solve for x here, I have to get it out of the denominator first, so I'm going to multiply by that entire expression in the denominator, and when I do that, it'll cancel on the right-hand side, and the left-hand side, it'll just remain 0. So I have 0 equals 5, which is clearly not true, so the x-intercept does not exist. For the y-intercept, when I plug in x equals 0, I have 5 over negative 1 squared times 3. So 5 over 3 gives me a y-intercept of 5/3. I will have two vertical asymptotes. One is going to exist at x equals 1, and the other will exist at x equals negative 3. So they came from here, setting that denominator equal to 0. Now for the horizontal asymptotes, the bottom is heavy, so the line is steady at y equals 0. So I'm going to begin here by plotting the y-intercept 0, 5/3, so it's a little larger than 1. And I have a vertical asymptote at x equals 1, and I also have another vertical asymptote at x equals negative 3. Now we know from yesterday that we should have 3 total branches now for this particular graph. I also have a horizontal asymptote, which I'll do in blue, at y equals 0. Alright, from here we're supposed to sketch our branches. Now based off the fact that I have that y-intercept here and my asymptotes are located where they're at, I'm going to draw my first branch in like this. Okay, now the reason why I know it has to look like this is because it can't go through that y-axis, or the x-axis, because I have, one, a horizontal asymptote there, but also because I don't have any x-intercepts for this particular function, so it can't cross the x-axis. Now, I also know that as x gets closer to 1, so as it approaches this value 1 here, that function's going to blow up, and that's why it's going to go towards positive infinity. As it approaches negative 3, it's going to also blow up and go towards positive infinity. Now for the remaining branches, because I know there's a total of 3, I can plot points. I can plot a point to the right of the line x equals 1, and I can plot a point to the left of x equals negative 3 and see where that point is. If I have a point up here, then the branch is going to be up here. If I have that point and it's down here, then obviously my branch is below. But instead of plotting points, because that's actually not a very efficient method, I'm going to do something different. I'm going to rely on the fact that I can look at the multiplicities of my factors in the denominator to see the behavior of the function as it approaches the asymptotes. Now I know that was a lot of words, so let me break down what I was just saying. Now our denominator has two different factors, x minus 1 squared and x plus 3. Now x minus 1 produced the vertical asymptote at x equals 1, and from x plus 3 we know that there's another vertical asymptote at x equals negative 3. So we have one at x equals 1 and one at x equals negative 3. Now, we say that x minus 1, this particular factor, has an even multiplicity because it's raised to a power of 2. So if that was raised to a power of 4, that would still be another even multiplicity. Okay. Now, x plus 3 is an odd multiplicity. It's raised to a power of 1, so this would be an odd multiplicity. Now, because of those multiplicities, I know how the function behaves at those particular vertical asymptotes. So at the vertical asymptote x equals 1, I'm going to have this particular behavior pictured below. Now again, it's because our factor that led us to that particular asymptote x equals 1 is an even multiplicity. Now at an even multiplicity, the behavior of your function as it approaches your asymptote on both sides, so on the left or the right side of your asymptote, will tend towards the same direction. So they'll either go to positive infinity together or they'll go to negative infinity together. Okay, so when I look at my graph here and I have this branch in the middle that I know I have to graph there, well, at the line, or at the vertical asymptote x equals 1, see how this is going to positive infinity? Okay, this is going to positive infinity. Well, the other branch then has to also go towards positive infinity in that direction, which means I can't draw it down here. Okay, because at x equals 1, they're supposed to both go up together, or they could go down together. But since this one's already going up, on this side of the function, it also has to go to positive infinity. Okay. Now, at the asymptote x equals negative 3, this had an odd multiplicity. And like I said yesterday, those are going to go in opposite directions. So at x equals negative 3, the other branch has to be down here below the x-axis. Now, just in case you want to verify that that's actually true, you can always plug in values. So let's say I plugged in the point x equals 2 into my function. So I have 5 over 2 minus 1 squared times 2 plus 3, which is 5. So I have the 5's here will cancel, and I'll end up with 1 over 1 squared is 1. So I have a positive 1 here. So the point 2, 1, so really I guess my branch should have gone through that coordinate here. But as you can see, it's above the x-axis also, so it's positive. It's in the positive quadrant here. And likewise, I can always plot a point to the left of this vertical asymptote x equals -3. Let's say I plug in the point x equals -4 into my function. Now I have 5 over -4 minus 1 is going to give me -5 squared times -4 plus 3. So if I just evaluate this, I have, let's cancel out the 5 at least. So it's going to be positive, and that'll be negative. So I have -1/5. Okay, so as you can see, the point -4, -1/5 is going to be below the x-axis, which is why this other branch here is drawn below the x-axis as well. So, moral of the story, if you know your even and odd multiplicities and how that affects the behavior of your function at those vertical asymptotes, it's a lot quicker to graph because you don't have to plot so many points. All right, in example 2, it's already been factored for me, so I'm going to cancel out the common factors, x plus 4. Now, I also see that I can cancel out an x minus 1 here, so my function is going to just be 1 over x minus 1. Now be careful that you don't say that there is a hole at x equals 1, because if you try to evaluate f of 1 here in your function, your new function here, you're going to get 1 over 0, which is undefined. So there's definitely not a hole there, but there is a hole at x equals -4. So at x equals -4, f of -4 is going to equal 1 over -5, so we have the hole at -4, -1/5. My x-intercept does not exist, because if I set y equal to 0 here, I end up with 1 equals 0, which is not possible. For my y-intercept, if I plug in 0, I have the y-intercept at 0, -1. For my vertical asymptote, I have a vertical asymptote at x equals 1, and for my horizontal asymptote, because the bottom is heavy, the line is steady at y equals 0. All right, so let's start graphing the information here. I have a vertical asymptote at x equals 1 and a horizontal asymptote at y equals 0. So I know I'm going to have 2 branches here because I'll have one more than the number of vertical asymptotes. So I'll have 2 branches. Now I have a y-intercept at 0, -1, and I have a hole at -4, -1/5. So -4, -1/5 is about right here. This is clearly indicating to me then that one of the branches should be here. Now because this is an odd multiplicity, so x minus 1 is to the first power, on the other side of that asymptote, I know that the function should behave as follows. So that's the end of the graph for number 2. All right, next up is number 3. And number 3 is specifically on here because we've got 4 terms in our numerator. Now, I don't want you to forget how we factored, in the previous chapter. So anytime you see 4 terms, remember you're trying to group 3 and 1, 1 or 3, or 2 and 2. If none of those work, then you're going to go to factor theorem. Now in this case, if you look, it's kind of giving you a hint here. If the denominator is x plus 6, one of the first things I'm going to test is to see if -6 is a 0 of this function here. Okay, so if I try -6 using synthetic division, let's use 1, 8, 9, and -18. Whoops, that's 1, -6, 2, -12, 3, and +18. It looks like -6 then is for sure a 0 of the function because I have a remainder here of 0. So I have a factor now in the numerator here. X plus 6 is a factor of this particular polynomial. Now left over is the quadratic x squared plus 2x plus 3, which I can factor as x plus 2. Oh, I'm sorry, x plus... oh, whoops, that's a -3. That's why I messed that up. Okay, so this should be x squared plus 2x minus 3. That's why it wasn't factoring. Okay, so x plus 3 and x minus 1 will be the 2 factors there. So there's my numerator now factored. So again, when you see 4 terms, try to use factor theorem and then use the hint that the denominator might help you. So I would just jump right away to trying -6 here. All right, now the x plus 6's obviously cancel, which will create a hole. So I'm going to plug in -6 into the resulting function, which is x plus 3 times x minus 1. Now, I hope you're realizing, just like in our example yesterday where it ended up being a line, this is just a quadratic. Okay, this is a quadratic function, and that's the standard form of that quadratic function. Now, if I plug in -6, I'd get -3 times -7, so positive 21. So there's where a hole is going to occur. Now, to find the x-intercepts, since we studied quadratics really extensively, it shouldn't be a surprise to you that we have an x-intercept at -3 and 1 at x equals 1. For the y-intercept, if I plug in 0 into the function, I should have the y-intercept being -3. Okay, and that just goes back to the standard form. It's easier to identify. But there are no vertical asymptotes here because the denominator has disappeared. It's over 1, so there are none. Or I guess I should write does not exist. And for the horizontal asymptote, same thing. If you want to think of it in terms of our rhyme, you have x plus 3 times x minus 1 over 1. So you've got, you big on top, just stop, because there ain't no horizontal asymptote. Yep, I did it again. I'm a loser. But anyhow, when we graph this function, I'm going to have two x-intercepts. So one at -3, one at 1. And I have a hole, I'm just going to indicate, since I know it's off the graph here, there's my hole at -6, positive 21. I have a y-intercept at 0, -3. And now I just need to find the actual vertex of this, because that's a review for you guys anyhow. Remember to find the vertex of your quadratic. Take opposite of b over 2a. So if I plug in opposite of b over 2a here, I have -2 divided by 2 times the a value here is 1. So we have an x value of -1, and if I plug that back into my function, I end up at -4. So that's the quadratic there, the graph of number 3. All right, next up is number 4. In this case, when I try to factor the denominator here, I notice that none of the methods that I would rely on, in the previous chapter would work here except for factor theorem. So the numerator here kind of gives me a hint. I'm going to try 2 and see if 2 is a root of this particular polynomial. So I use 1, 5, -8, and -12. And just by synthetic division here, I end up with 2 being a factor, or I'm sorry, 2 being a root, which means that x minus 2 is a factor for this particular polynomial, okay, because I have a remainder of 0. Now, the leftover polynomial here, this quadratic, is x squared plus 7x plus 6, which will be really easy for me to factor. That's just x plus 6 times x plus 1. Now, in the numerator, if I rewrite this function with all of the terms, clearly that x minus 2 in the numerator will cancel with the denominator. So I will have a hole at x equals 2. So in my resulting function, I have f of x equals 1 over x plus 6 times x plus 1. So I'm going to plug in x equals 2. So I have 1 over 8 times 3, which is 1/24. So I have a hole at 2, 1/24. Now I'm going to kind of fly through the rest of the stuff. I have no x-intercepts here. The y-intercept, if I plug in 0, is going to be 6, or I'm sorry, 1/6. So I have 0, 1/6. My vertical asymptotes are at x equals -6 and at x equals -1. And because the bottom is heavy, the line is steady at y equals 0. Now, based off of this information, I'd like you guys to try to sketch this before I do it with you, just to see if you actually know what you're doing. So go ahead and pause the video and try to sketch this out. All right, so I plotted some of that information, and I know that that hole 2 1/24 is so close to the x-axis. Just make sure you write it above, or you draw the hole above it. Obviously, it can't be that accurate, but that's definitely where one of the branches is going to be. Now, to find the other branches, I'm going to look at the multiplicity of the actual asymptotes. So this asymptote here is x equals -1, which means I'm going to look at the factor x plus 1 here, and that has an odd multiplicity, which means that at that particular asymptote, the behavior of the function, it's going to go in opposite directions. So one will go towards positive infinity, the other will go to negative infinity. So that other branch here has to be below the x-axis. Okay. Now I'm not drawing it through that asymptote because there are no x-intercepts here, so it's not going to cross that horizontal asymptote. Then for the other branch, I'm going to look at, since this is the vertical asymptote x equals -6, I will look at x plus 6. Again, it has an odd multiplicity, so this should go in opposite directions as well. This one's going down, so the other one will go to positive infinity. So there's the other branch, and that's example 4. All right, in the next couple examples, we're actually going to see some graphs of rational functions that actually go through their horizontal asymptote. Now, I know that's kind of counterintuitive to what we've told you since the beginning of the year. When we defined asymptotes before, we said, it's a line that your graph doesn't cross. It gets really, really close to it, but it never actually crosses or equals that value. But that's actually not entirely true for horizontal asymptotes. So let me explain a little bit here so you don't think I'm a liar for telling you that you can't ever cross an asymptote, because you can't ever cross a vertical asymptote. All right, if you read this little note here, you can never cross vertical asymptotes, so we should never see a graph of a function if we have a vertical asymptote here. You shouldn't draw it like that ever. Okay, that'd be a big no-no. But it is okay to cross a horizontal asymptote because a horizontal asymptote only tells you the long-run behavior of your function, meaning it tells you the behavior of your function as x gets really, really big. So as x goes towards positive infinity or as x goes towards negative infinity. Okay, those are your long-run behaviors of your function. So at those particular values, really large values and really small values, your graph will not touch your horizontal asymptote. It gets closer to it, but doesn't actually cross it. So horizontal asymptotes are going to tell you the long-run behavior of your function past those vertical asymptotes and the x-intercepts, but it won't tell you what it behaves like in the middle of your function. So your function kind of does what it wants, okay? Sometimes it actually crosses the horizontal asymptote, which will usually be indicated with either a y-intercept or an x-intercept. You can actually see that it crosses that horizontal asymptote. So those are the kind of problems that we're going to work on now. So let's take a look at number 5 here, which is actually almost identical to problem number 2 on the beginning of our note sheet. I just changed a couple signs. Now those sign changes here, it used to be x plus 4 and x minus 1. Those small details here completely change the look of this particular graph. So you have to be really, really detail oriented when you work on these rational functions. All right, so anyhow, there are no factors that cancel, so I will have no holes. Now for the x-intercepts, I have an x-intercept at 4, 0 and one at negative 1, 0. And let me just move this up a little bit. For the y-intercept, I should get negative 1 when I plug it in, so I have a y-intercept at 0, negative 1. For the vertical asymptotes, I have a vertical asymptote at negative 4 and at x equals 1. For the horizontal asymptote, this time since it's factored, it might be a little tougher for you to find the horizontal asymptote, but you still have to compare the degree of the numerator to the degree of the denominator. Now, if you were to multiply out the numerator, that lead coefficient is going to be 1, and then the term is x squared. In the denominator, if you multiply out, this has 3 different factors here, and I don't really care about multiplying all of them. I just want to know what the first terms here multiplied would give me, and it would give me a positive 1x cubed here. So the bottom is heavy, okay, which means that I don't even need to pay attention to the coefficients, because if the bottom is heavy, the line is just steady at y equals 0. So that's where my horizontal asymptote is. Now I'm going to pause and then just graph all of this information. Alright, so there's the start of my graph just based off of this information here. Now as you can see, the horizontal asymptote is being crossed at x equals negative 1 and at x equals 4. When you draw in your branches, you got to pay attention to where those points are located. So I want to make sure I'm hugging the asymptotes. The easiest branch to draw here is going to be the one in the middle first, because I see that I've got this value here, which means that my graph should look like this. Okay, it can't come from above, cross through, and then come down like that, because it's not a function then. I have y values on top of other y values, so that's not going to work. So it's going to go through and up to the other asymptote. Now I also wouldn't want to draw it in, let me erase this real quick. I also wouldn't want to draw it in like this, because then it's crossing the x-axis twice, and it's not supposed to. It's only supposed to cross there once. So that branch that I have drawn in first is the only way that that graph can actually abide by all of the information that we've found so far. All right, now on the other side of this particular asymptote, remember this is the asymptote x equals 1, which came from that denominator factor x minus 1 squared, which has an even multiplicity. So at that particular asymptote, the behavior of your function should approach it in the same direction. So on the other side here of this asymptote, it should also tend towards negative infinity, which means it's going to come up, it's going to cross at x equals 4, and then it's going to come back down and hug the rest of the graph here as it goes towards positive infinity, or I'm sorry, hug the asymptote as it increases to positive infinity. Okay, so there's my other branch. Now to find the third branch here, which is going to be on the left side of the asymptote x equals negative 4, this one, if I look at x plus 4 here, that has an odd multiplicity, so these should go in opposite directions. So this branch should go to should be coming from negative infinity and go like that. And there's your sketch. So it doesn't have to be beautiful, and you don't have to find specific values as long as you understand the concept of the multiplicities. All right, just to save some time, I actually went through and found all the information, and I graphed the parts as well. You're more than welcome to pause the video and try to see if you can do it on your own. I'm just going to talk you through this because I think the most important thing is making sure you understand how to draw your branches. Now I do want to point out that to find that horizontal asymptote, it's at y equals 2 because the degrees of the numerator and the denominator are the same. They're both 2. So then I look at the coefficients, 2 over 1, so I have a horizontal asymptote at y equals 2. Now I just want to mention that the horizontal asymptote here is at y equals 2, and that's because if you look at the degree of the numerator and compare it to the degree of the denominator, they're the same. So then you look at your coefficients, 2 over 1, which gives you a horizontal asymptote then at y equals 2. Then from the points that I've graphed, the purple points here, you can clearly see that one of those points is crossing that horizontal asymptote because I have a y-intercept at 0, 2. So when I graph this first branch here, I know that because I have this other x-intercept here, and because it's crossing that horizontal asymptote, the branch would look like this. Okay. Then, because I have this other coordinate, the other x-intercept at 4, 0, I know that the other branch here to the right of x equals 3 should look like that. And it's also consistent with what we've talked about with even and odd multiplicities, because if you compare, remember this asymptote here is x equals 3, which came from the factor x minus 3. So if you compare its the multiplicity here, which is 1, these should go in opposite directions, and they do because it's an odd multiplicity. Then for the other branch, let me switch back to blue. On the left-hand side of x equals negative 4, you can come back to this and say, okay, that's to the first power as well, so it's an odd multiplicity. So it should be on opposite sides. So the other branch here should be above the line y equals 2. Alright, we're almost finished, guys. For number 7, I went ahead and found our information, and I just want to point out that there are no vertical asymptotes here because x squared plus 4 can never equal 0. So I have no vertical asymptotes, which means I only have one branch in this particular function. Now, because I have a y-intercept here above that horizontal asymptote, I know my graph has to at least go through that point, okay? And when you think about the long-run behavior of this function, remember, it's going to hug your asymptote as you get larger in the negative direction, so a really large negative number or a really large positive number. It's going to hug that horizontal asymptote. So that's actually the graph for number 7. Alright, we're to the last problem in the lesson. So here in number 8, if you want to try this one on your own, you're more than welcome to. I still will work through this though because I think it's a bit tricky, so go ahead and try it and check with the key to see if you got it right. Alright, the first thing I want to do is look for holes. There are none, because none of the factors cancel. I do have an x-intercept here. When I plug into the function y equals 0, I end up with 0 for the x-intercept 0, 0. So that means the y-intercept here is also 0, 0. There are no vertical asymptotes because the denominator here will never equal 0. If I set that equal to 0, I know that that has no solution for a real x value, so it does not exist. Now for the horizontal asymptote, I'm going to compare the numerator's degree to the denominator here, and they're the same, which means I look at the lead coefficients. So that lead coefficient would be 5, and here in the denominator would be 1, so we end up with 5 divided by 1, which is 5. So I have a horizontal asymptote at y equals 5. Alright, now based off of that information that we found, this would be the graph so far. Now, you're going to have to think about the long-run behavior of your function in order to complete this graph. Remember that you're going to have one branch because you don't have any vertical asymptotes, and as x gets really, really big, it's going to have to hug that horizontal asymptote. As x gets really, really small, it's also going to have to hug that horizontal asymptote, but it's also going to have to go through this coordinate. So the best way to graph this, as x gets larger, it's going to hug that asymptote, and as x gets smaller, it's going to hug that asymptote. So there's the graph. Again, it doesn't have to be beautiful, it's just a rough sketch. So that is the end of the lesson, guys. Nice job. Thanks for sticking in there. I know it's another long one. Tomorrow you're going to get practice with these more difficult problems, and then on day 3 we're just going to go through a lot more review with you just so you can be ready for that quiz. Alright, nice job. See you tomorrow.